This is the Spring 2019 final exam for MA 265. I thought that I had this one done already, so I was planning on getting the last one done right about now, which is fall 2019, but yeah, no, I had that wrong. So we're doing spring now. Let's get going. Question 1. The matrix below represents the augmented matrix of a system of linear equations. We're told that the variables we're dealing with are x1 through x6, and we have our coefficient matrix here. We're trying to figure out which of the following statements are true. 1. For any given C and D, which only show up here and here, the system above is consistent. So our system will be consistent as long as we don't get any 0, 0, 0, 0, 0, all zeros is equal to something that is not 0. So it doesn't matter what C and D are here. They could be 0, they could be a non-zero value. Our system will still be consistent. Is our coefficient matrix A in reduced echelon form? Well, we fulfill kind of the first requirement of echelon form, where we have this stair-step pattern of our pivot positions. So we have a leading one here, a leading one here, and two leading ones here. But above all of these leading ones, we should have a column of zeros. And right here, we have a 1 where there should be a 0 because we have a leading position below it. So therefore, we're not in reduced echelon form. Whoops, sorry, gotta fix some things. There we go. The right-hand side vector is in the column space of matrix A. So we just saw from 1 that for any given value for C and D, the system will be consistent, and by definition, anything in the column space is some matrix B that satisfies AX equals B. And since this vector, no matter what its C and D values are, will be consistent for AX equals B, thus it is in the column space of A, which is just the span of our columns. What about 4? The system has no solution. No, clearly the system does have a solution. You can read this as if you take 1x1, 1x3, 2x4s, you'll get 1, and you can read that off for the other columns. Clearly, we do have a solution here. So no, that's not true. But does the system have infinitely many solutions? Well, yes, it does, because we have 1, 2, 3, 4 pivot positions, but there are 6 columns. So the rank of our null space is 2. You could go down that route to say that the system has infinitely many solutions, but that's only really for the solutions for AX equals 0, but this is not the 0 vector. So really what we would have to say is because it's consistent for any values of C and D, we can have an infinite number of combinations of C's and D's that still keep the system consistent. Thus, the system will have infinitely many solutions. So 1, 3, and 5 are correct for number 1. That's D. 2, we have a set that is linearly dependent. Let's find A. So making a matrix out of this, 1, -2, -1, -3, -2, -2, 1, A, 1. We can flip all of, oh god, that keeps happening. Sorry about that. It won't happen again. I turned the sound off. There we go. So if this set is linearly dependent, when we reduce it down to echelon form, we should get 2 pivot positions, which means that there should be a row here that we can set to all zeros, so that we have no pivot in that row. And just by looking here, if A is equal to 2, then we can take row 1, subtract it from row 3, and by definition, we will have a linearly dependent set because we're left with 3 vectors that are only working in with the two remaining dimensions. And even if we have two linearly independent vectors in R2, they by definition span all of R2, so there's no place to put a third vector without already being in the span of the first two. So A is equal to 2 is our solution for 2, that is C. 3. Which of the following statements is false? If the set V1, V2, V3 is linearly dependent, then V3 is a linear combination of V1 and V2. So you got to be really careful with this one, because this is not necessarily true. Let's kind of think about what we were talking about right up here with this graph of R2. Let's say that we have a vector V1, and then we have a vector V2. V3 is a linear combination of V1 and V2. Well, if V1 and V2 span all of R2, then that would be true. But what if V1, this is just one of the kind of counterexamples that you can make here. What if V1 and V2 are both on the origin? Then, if they're both the 0 vector, it doesn't say that they can't be in the question, so then any V3, by definition, is, I keep saying that, this is the third time I've said that in like 3 minutes. V3 is not a linear combination of V1 and V2 because there are no constants you can multiply by V1 and V2 to get anywhere out of the origin. But still, this set is linearly dependent because we have V1 and V2 that are combinations or multiples of each other. So A is false. Let's talk about why the other ones are true, though. B, suppose that the columns of A are V1, V2, V3, then the matrix equation here is equivalent to this vector equation. So that's just a result of matrix multiplication. They're saying we can replace A with V1, V2, very sloppily, V1, V2, V3. Multiplying these out, our first term will be V1 times X1, then plus V2 times X2 plus V3 times X3. And that's exactly what they get over there. So for number C, C is not a number. For C, I don't exactly completely understand what's going on, but I'll do my best to explain what I do know. So suppose that x0 is a solution to this linear system ax equals b. Then the set of all x that solves ax equals b is equal to x0 plus the set of all x that solves ax equals 0. So let's think about this geometrically really quick. If we have some transformation that takes in all of R2 and spits out a line in R2, then what we can say is that transformation has a rank of 1 because we went from from 2 dimensions down to 1 dimension, and as a result, the nullity must also be 1. Because the nullity is 1, we can see that there should be an infinite line of vectors that gets squished onto every single point here from each direction. So each one of these has 1, 2. We know that the null space is the set of all solutions such that the set of all vectors such that their transformation leads to the origin, and that would be anything on this line here. So what we can do is if x0 is a solution for, and I'll get rid of the ones that we don't need really quickly. Let's say that x0 is a solution to, there we go, to ax equals b. Let's say that b is right here, and x0, okay. Let's say that x0 is a solution there. If we want to get the entire set of all of the vectors that end up at b, what we can do is add the set the set of vectors such that ax equals 0. And essentially, it seems like what we're doing here is just translating this set of solutions all the way up to the location of b, because x under this transformation we know will land at b, and then if we add that to all of these vectors that we know end up at 0, that will just, under our transformation, put us right up here. So we've just generated, in a way, this entire set of vectors by adding x0 to all of the solutions to our null space. So super weird. I'm not really liking that one, but let's move on. D, the columns of A are linearly independent if and only if A has a pivot position in every column. A has a pivot position in every column. Well, yep, that's true, because, well, I don't really need to show that much. Let's say we have a 2 by 3 matrix, 1 0 0 1 1 1, like that. We know that any set of vectors in R2 can only be linearly independent if there are fewer than or equal to 2 vectors, and that's because what we were saying up here, if we have 2 linearly independent vectors in R2, there's no place to add a third one, where that third one will not already be in the span of the first 2, which by being linearly independent already span all of R2. So essentially, we need a pivot in every column, and that is directly determined by how many rows we have, and therefore the dimension of our output space, in this case R2. So that is true. And by crossing this off, really it's true. Okay. What about E? A homogeneous linear system has a non-trivial solution if and only if it has at least one free variable. So the homogeneous system would be of the form ax equals 0. That's our null space, and we know that the null space's dimension, or let's see, if the null space has a non-trivial solution, that means it has a dimension greater than 0. And we know that the dimension of the null space, the nullity, is equal to the number of columns minus the number of pivot positions. And if we have a free variable, that's the same thing as saying that we have one fewer pivot position than we have in number of columns. Thus, our nullity will be non-zero, so E is true. So 3, after all that, is A. Let's sum linear transformation from R2 to R3 B, such that the linear transformation of 1, 2 gives us that vector, and 3, 2 gives us that vector. So one of the properties of linear transformations that we know is that L of x1 plus x2 is equal to, and really they like it better as t. Okay, sure. The transformation of x1 plus the transformation of x2. As a result, we can just figure out what linear combination of 1, 2 and 3, 2 makes negative 1, 2, and then add that same linear combination of the output vectors, and we will have our solution. So we're solving an augmented matrix here with 1, 2, 3, 2, negative 1, 2. To find the values of x1 and y1, we need to make negative 1, 2 out of these two vectors here. Let's reduce this down to 1, 1, 1 and subtract it. Subtract it from row 1, 0, 2, negative 2, so 1 and negative 1, 0, 2. So we need 2 of these guys, and we need negative 1 of our second ones. So all we need to do is add 2 times 0, 1, 4 to negative 2, 0, 1. That gives us 2, 2, 7. So B is our answer for 4. 5. Let L be a transformation from R2 to R2 whose standard matrix is given there, where T is a real number. Find all values of T such that L is 1 to 1. Well, if L is 1 to 1, it means that the columns of L are linearly independent. There we go. And excuse me, if the columns of this standard matrix are linearly independent, that means that when we reduce it, we must get 2 pivots. So let's take this matrix, T minus 1, 1, 2T minus 2, T, and see where that happens. Let's add row 2 to row 1, like that, and then what values would this not work for? Okay, actually I shouldn't really have done that. Let's subtract 3 row 2's from row 1. It gives us minus 3 and 0 there. Okay. Interesting. So we don't want these rows to be linear combinations of each other, or multiples of each other, because then we could take one row and add some multiple of it to another row and get 2 zeros. So where does that occur? It's actually kind of difficult. It's kind of difficult to tell. Well, worst comes to worst, we can always check some of these answer choices here. So if t is equal to 1, for t is equal to 1, and I really wish I could give a better explanation here. If for t is equal to 1, we will get negative 2, 1, and 1. Okay, well that's definitely a value that L will not be 1 to 1 for, because we can reduce this to 1, 1, and use it to set this row to 0, 0. And because we don't have 2 pivots, our matrix is not linearly independent. Thus, L is not 1 to 1. So t not equal to 1 is one of our solutions, definitely. For t is equal to 0, our rows will not be linear combinations of each other. You can try that out for yourself, but I can just see that from here. What about 2? That seems like the last one that we need to check. For t is equal to 2, we will get negative 1, negative 2, 1, 2. Well, there you go. You can use row 1. We can add row 1 to row 2, and we'll get a row of zeros. Thus, for that value, L is also not 1 to 1. So t not equal to 1 and not equal to 2 should be our solution. 5 is C. 6, here we have A. We're finding the trace of the inverse of A, so the sum of the main diagonal elements of A. So what we'll need for this is the determinant of A. We can find this determinant by noting that since 1 is in a column by itself, we can take the determinant of the matrix formed by crossing out that row and column and multiply it by 1. But make sure that we take this into account, that 1 will have a sign on it based on its position in the matrix, plus, minus, plus, minus. So it will have a minus sign. And the whole scheme for that, if you remember, is plus, minus, plus, minus, plus, minus, plus, minus, plus. So however you want to remember that, that is what works. So negative 1 and 2, 1, 2, 2. This gives us 4 minus 2 in there, so a determinant of negative 2. So now if we're finding the sum of some values of the inverse, all we have to do is take 1 over this determinant, because finding the full inverse, we have to multiply by 1 over the determinant of A outside. So all of our entries individually will be multiplied by this, so 1 over negative 2. And then we will need 3 individual cofactors. So our cofactors will have a sign going by this scheme, and if we want the cofactor for the 1, 1 position, we have to In this case, we don't have to switch anything, but instead of doing 1, 1, or let's say 2, 1, if we were looking for the 2, 1 cofactor, we would have to do the process that I'm about to do for the 1, 2 position of our matrix. So let's do that. For 1, 1, we switch the order, we get 1, 1. So we take the 1, 1 position in the matrix, cross out its row and column, and take this determinant right here and make sure to add the sign of the 1, 1 position onto that. So we get -2 for that determinant. Then for the 2, 2 position, still has a plus sign, and we get 0 for that, plus 0. And then we have a plus sign for this -3 position. We cross both these out. We get a determinant of 0 for the matrix that's left over. And so we are left with +1 as our solution, D for 6. 7. Let's find the third column of the matrix D, given that C is there and that CD is given here. So since this matrix that we're getting out is 2 by 5, and this guy is 2 by 2, what should the dimensions of D be? So we have 1, 3, -1, 2 times D is equal to 2, 0, 0, 3, -2, 1, 1, 7, 0, 0. Well, we don't really actually need to figure that out. That'll come in the end, because what we can do is multiply both sides on the left by the inverse of this matrix here, and we'll be able to solve directly for D. So C inverse is going to be 1 over the determinant of C, which is 5, multiplied by what we get by swapping the A and the D positions, so 2, 1, and then switching the signs, -3, 1, of the B and C positions. So we can grab this matrix, multiply the left side of our equation by that. Okay, gotta be careful here. Gotta rearrange some things. Make that smaller. Multiply. So we have to be careful, because multiplying these two together, multiplying a matrix by its inverse will just give us the identity matrix. So all of this we can get rid of, but we still have this 1 over 5, which is an easy factor to get lost on that other side. So now we're multiplying a 2 by 2 matrix by a 2 by 5 matrix. So we will get a 2 by 5 matrix out. And you'll see that we are looking only for the third column of D, which we will get by multiplying these components together. The top row of this guy, of C inverse, times the third column, dotted with the third column of D will give us the top position, and then likewise using the bottom row of C inverse for our other position. So we have D call 3 is equal to 1/5 times -4 plus 1, so -3, and 6 plus 1, so 7. That gives us answer choice B for 7. 8. A is an n by n matrix. Which of the following statements is necessarily true? If it's not so ingrained in your head that you think about it in your sleep, the rank of A is the same as the rank of A transpose. That is, well, if there were 10 commandments for this class, this would probably be right up there, with the no, you know what? This would be the 11th commandment after the 10 statements of the invertible matrix theorem, probably. But yeah, that's just true. We really don't need to go through any of the rest of these, but I will just for the sake of completion. So A, the nullity of A is the same as the nullity of A transpose. Nope, not true. So the rank will always stay the same, but if we have an m by n matrix with m not equal to n, that means the columns of the matrix are not equal to the rows of the matrix. And since our equation for nullity is rank plus nullity is equal to the number of columns, that will change when we transpose our matrix. The rank will not, so n will have to change to compensate. The column space of A is the same as the null space of A transpose. Nope, not true. This is a whole different vector space that I want the video calling it the left null space, but I think we just call it the null space of A transpose. Yeah, these two have not much to do with each other. They're two very different subspaces. For D, the columns of A form a basis of the column space of, for a basis for the column space of A. No, untrue. If we have even a matrix like this right here, the maximum number of pivots we can get is 3. If we have 3 pivots, we know that the basis for the column space of that matrix corresponds with the original 3 columns that we had, the original 3 pivot columns before we did any row reduction. But what that means is that these other two cannot be in that basis set because we only need 3 vectors to span R3, and thus these two will just be adding nothing to the party. What about E? The columns of A transpose form a basis for the null space of A. Nope. The columns of A transpose form no, they don't. The columns of A transpose don't have to do anything. Yeah, no, that's just wrong. Okay, but that means that 8 is B. Here is 9. Let's find a basis for the null space. 1, 2, 2, 2, 2, 3, 2, 3, 1, 3, 3, 1, 2, 2, 2. Let's row reduce this thing and get it into a form where we can pull some equations out of it. And really, we're setting this equal to 0, 0, 0, but those zeros never change, so I really don't bother writing them. Let's subtract 3 row 1s from row 2. That gives us 0, -4, -3, -5, -3. I'll change all of those signs around. And then let's subtract 3 row 1s from row 3. That gives us 0, -5, -4, -4, -4, but I'll just go ahead and make all of that positive anyway. What can we do now? Let's subtract row 2 from row 3. That gives us a 1, a 1, a -1, and a 1. Let's subtract 2 row 3s from row 1. That gives us a 0, 0, a 4, and a 0. Let's subtract 4 row 3s from row 2. 0, -1, 9, and subtracting 4, right? So -1, flip those signs. Let's subtract row 2 from row 3. That gives us a 0, an 8, and a 0. And it looks like we are good. If I rearrange these rows to a echelon form that we're more, well, here we go. We have a reduced echelon form, actually, something we're a little more familiar with. We can see that this top row says if we take all of these guys and move them over to the right-hand side for all of our free variables, because since we have a pivot for x1, x2, and x3, x4 and x5 must be free. x1 is equal to -4 x4, x2 is equal to -8 x4, x3 is equal to 9 x4 plus x5, x4 is equal to x4, and x5 is equal to x5, just to keep that clear there. So now we can make 2 vectors. If we make an x4 vector, x1 is equal to -4 x4, -8 x2, 9, 1, 0. And then x5 is equal to 0, x1, 0, x2, 1, x3, 0, x4, 1, x5. And oh, look at that. I messed that up when I subtracted 1x5 over for x3. I forgot to make it negative. So there's our -1, and we get A as our answer for 9. Suppose a 3 by 3 matrix A given here has a determinant of 4. What is the determinant of this thing? So we know that when we add a multiple of a row to another row, it doesn't actually change our determinant. So we can get rid of that operation there without changing anything around. So what do we do? What do we need to do now to get from this matrix, which we know the determinant of, to get to this matrix that we don't know its determinant? Well, we see that we have ADG here and AGD in that first column. So what we'll need to do is switch those two rows, and that will take our determinant of 4 and multiply it by -1. Now we have ADG, B, nope, 2B, 2E, 2B, 2E, no, 2B, 2H, 2E, and CIF. Now the only difference that we have left is that we have a column multiplied by 2. That will have multiplied our determinant by 2. So we can get rid of that. I'm sorry, I'm not being particularly clear here. Let's remove that. So this is what we have here is our matrix A after we switch two rows and after we switch two rows. That's fine. Now the only thing we have left to do that we know changes our determinant is multiply this column by 2. And multiplying a column by 2 multiplies our determinant by 2, so we get -8 as our solution. And remember, the thing we crossed off in the beginning here is just a little extra thing that we could do on the end. I could add 100A, 100B, and 100C, and our determinant will not have changed at all. So 10 is C. Let's compute this determinant. We are going to be making use of the fact that if we have a value like 2 here in a row by itself, or a column by itself like it is here, we can cross out the row and the column that value is in and take 2 times the determinant of the matrix that we get by crossing out that row and column. But more importantly, we have to add a specific sign to that 2 that we pull out that's dependent on its position in the matrix. And for a 4 by 4 matrix, that is plus, minus, plus, minus, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus. That's great. So this 2 will have a plus sign. So we can say that this determinant is equal to 2 multiplied by this matrix, 0, -5, 0, 3, 0, 5, -4, 3, -7. Now we're dealing with a 3 by 3 matrix, so I'll shrink this guy down a little bit. And since -5 is in a row by itself and it has a sign of -5, we can pull out +5. So now we have 10 multiplied by 3, -4, 5, -7. That gives us -21 plus 20, which is -1 times 10 is -10. So 11 is B. Suppose that A is equal to PDP inverse, where P is a 3 by 3 invertible matrix and D is given there. It's diagonal. And, oh great, B is 2I plus 3A plus A squared. Which of the following is true? So, B is diagonalizable, or whether B is diagonalizable is something that we would really like to know right about now. And I had to go do some sizable digging to figure out these rules, but these all check out. That if we take a matrix, so A squared, the eigenvalues, let's say that the lambda 1 is an eigenvalue of A. Okay. If we take A squared, lambda 1 will become lambda 1 squared. If we take some constant times A, that will give us that same constant times lambda 1. And if we take lambda plus ci, so we're adding C times the identity matrix to A, lambda 1 will become lambda 1 plus C. So B is diagonalizable if the three eigenvalues that we get for B are all unique. If we have a 3 by 3 matrix with three distinct eigenvalues, it must be diagonalizable. And then we know that the matrix C here, the diagonal matrix, where B is equal to P, C, P inverse, will just be composed of the eigenvalues on the main diagonal, of B's eigenvalues on its main diagonal. So let's figure this out. If B is equal to 2i plus 3a plus a squared, that means that we're taking the eigenvalues of A, which are right here. So we're taking, so we're starting out with lambda 1 equals 1. B's first eigenvalue that comes from this eigenvalue of 1 will be 2 plus 3 times 1 plus 1 squared. So that is 6. Then for lambda 2 is equal to 2, coming from right here, we can see that this will be, so 2i, which is, we're adding 2 to our eigenvector, plus our eigenvector times 3, so that will be 3 times 2 plus our eigenvector squared, which gives us 4 plus 6 plus 2, which is 12. Then for negative 3, lambda 3 equals negative 3, we get 2 plus 3 times negative 3 plus negative 3 squared, which is negative 9 plus 9, yeah, plus 2, so we get 2. So the eigenvalues of B should be 6, 12, and 2, and since we have three distinct ones, B must be diagonalizable, and its diagonal matrix must look like that. So B is our answer for 12. Which of the following statements are true? If lambda is an eigenvalue for A, then negative lambda is an eigenvalue for negative A. Well, what were we just talking about? If we take C times A, then our, and if lambda 1 is an eigenvalue, is a member of the set of all, oh, look at me trying to do math notation, is the set of, from the set of all eigenvalues of A, then CA will lead to an eigenvalue of C lambda 1. And since all this is really doing is multiplying A by negative 1, by this rule, this will be true. What about 2? If 0 is an eigenvalue of A, then A is not invertible. Well, yeah, that's true. We can think about this geometrically or by kind of writing it out. Let's make a 3 by 3 matrix. 1, 0, 0, 0. I'm not good at sizing these. 0, 0, 3, 0, 2, 4. So since we have an upper triangular matrix, the determinant of this matrix is the product of its main diagonal, which is 0. So we know that this matrix is not invertible, and we also know that its eigenvalues are just these elements on the main diagonal. So 1, 0, and 3 are our eigenvalues. And we know that any matrix, any n by n matrix, is reducible to some upper triangular matrix like this, and thus if it is not invertible, 0 must be one of those elements on the main diagonal. And yeah, I hopefully you agree with me by this point. I'm kind of there's not much else to say for that one right there. You can think about it geometrically also, because an eigenvalue really means the factor by which vectors along an eigenvector get scaled. So what you can say is, well, lambda equals 0 really means that there's an entire vector that's getting scaled by a factor of 0, so it's all getting crushed down into the origin, and as a result, ax equals 0 will have non-trivial solutions, and therefore a is not invertible, because the null space will be greater than 0-dimensional. Okay, sure, fine. 3, if an n by n matrix A is diagonalizable, then A has n distinct eigenvalues. Nope, not true, because A can have fewer than n eigenvalues as long as the total dimension of all of A's eigenspaces adds up to n for r to the n. And we can get this result because let's say we have two eigenvectors and a 3 by 3 two eigenvalues and a 3 by 3 matrix. If one of those eigenvalues leads to two free variables in our matrix A minus lambda I, then we'll get two eigenvectors out of it. And all we're looking for is to have enough eigenvectors to span the space that our matrix lives in. So for R3, all we need is 3 eigenvectors, which we can get with fewer than 3 distinct eigenvalues. What about 4? There's A. It is both invertible and diagonalizable. Well, okay, invertibility doesn't imply diagonalizability, and diagonalizability does not imply invertibility. This thing is invertible because it has a determinant of 4, but is it diagonalizable? Well, our lambdas are going to be 2 with a multiplicity of 2, and when we plug in 2 to A minus lambda I, we will get the matrix 0, 0, 0, 1, and since that only has one free variable, we will only get one eigenvector. Thus, our eigenvectors cannot span R2, and A is not diagonalizable. So 1 and 2 are correct for 13. Let's define a transformation from R2 to R2 by t of x equals ax, where a is given there. Which of the following is a basis for R2 with the property that the beta matrix for t is a diagonal matrix? So, really what we have to recognize here is that this is just asking you to find the eigenvectors of A, because along an eigenvector, values, or an input vector is only scaled during a transformation by the eigenvalue corresponding to that eigenvector to reach your output vector. And blah blah blah, that really means that this expression A equals P dP inverse represents a change of basis from the normal basis for, in this case, R2 to an eigenbasis represented by the matrix P, where the matrix P transforms us into that eigenbasis. Then we scale by our eigenvalues, and then we undo that original change of basis into the P world, into the eigenbasis, back to the normal basis. So this really does the exact same thing that this matrix is doing here geometrically. So as a result, all we need to do is find the eigenvectors of A, and that will be exactly what we're looking for, a basis such that all we have to do is scale our eigenvectors by some value in order to get our result. And we know that this matrix in here that we're actually multiplying by our basis is exactly that, diagonal. So if I get rid of that, there we go. Solving for the determinant of A minus lambda I equals 0, we're solving 2 minus lambda times 3 minus lambda minus 6 is equal to 0. Lambda squared minus 5 lambda is equal to 0. Lambda is equal to 0 and 5. So for lambda equals 0, a minus lambda I will be 2, 3, negative 1, negative 6. We can simplify this to 1, negative 3, 0, 0, and get an eigenvector of 3, 1. For lambda is equal to 5, a minus lambda I will be negative 3, negative 2, negative 1, negative 6. We can simplify this to 1, 2, 0, 0, and get an eigenvector of negative 2, 1. So the basis formed from the set of these two vectors should be an eigenbasis, and thus it will have the property that the beta matrix for T is diagonal. So 14 is A. We have A here. We're trying to find A to the 32nd power. So let's diagonalize things. That will make our lives a little bit easier because A to the K is just equal to PD to the K, P inverse. And so all we'll have to do is compute the rest of this around that, around our diagonal matrix D, and we should be able to find A to the K relatively easily. So what are the eigenvalues of A? Well, we're solving the determinant of A minus lambda I, so negative lambda times negative lambda minus I squared. Minus I squared will be 1 is equal to 0, so lambda squared plus 1 is equal to 0, or lambda is equal to plus or minus I. For lambda is equal to I, A minus lambda I will be negative I, and I. And so what can we do with this? We can simplify this down to 1, negative 1, 0, 0, just adding row 1 to row 2 and then dividing row 1 by I. And so we get an eigenvector of 1, 1 from that. And what about lambda equals negative I? Well, A minus lambda I then will be I, which we can reduce down to 1, 1, 0, 0, and so we get an eigenvector of negative 1, 1. So therefore, we can write PDP inverse, where P is our two eigenvectors in an ordered pair, 1, 1, negative 1, 1. Then our matrix D will be the diagonal matrix with the corresponding eigenvalues on the main diagonal. So we have I, 0, 0, negative I. And then we need to multiply here at the very end by the inverse of this matrix here. The determinant of P is 2. So we have 1/2 outside. And then we'll switch the A and the D positions and switch the sign on the B and C positions. And now if we're looking if we're looking for A to the 32nd, that's just this guy to the 32nd, which is just 1, 1 in here. The identity matrix times anything is just that anything, so we can rewrite this as 1, 1, negative 1, 1 multiplied by 1, negative 1, 1, 1 times 1/2. This will give us, I'm getting pretty cramped for space. We should move this up here and take a little bit of the rest of the problem with. Okay, we should be able to compute this. This will be another 2 by 2 matrix, except I'm going to multiply this 2 over. There we go. What will we get? We have let's see. 2 here, 0 here, 0 here, and 2 here. So it looks like the identity matrix C for 15 is what we get. Yep. 16, we have a dynamical system, x prime equals ax, where a is given right there. What is the origin? So all we care about is the sign and types of eigenvalues of A. So solving for those eigenvalues, 1 minus lambda times negative lambda minus 2 is equal to 0. Lambda squared minus lambda minus 2 is equal to 0. lambda minus 2, lambda plus 1 is equal to 0, so lambda is equal to 2 and negative 1. When we have opposite signed eigenvalues like this, let's say that we have our eigenvectors here, what that means is that as time approaches, as time goes from 0 to infinity, values or initial conditions will follow one eigenvalue and then begin to follow the other eigenvalue as time goes on. And that's a result of the fact that as the solution associated with this eigenvalue, as t increases, this guy will be getting bigger and bigger, because our solution will be c1 v1 e to the lambda 1t plus c2 v2 e to the lambda 2t. And if we have a negative value up here, let's say that this is our negative t, here's our 2t, as t approaches infinity, this guy will be getting infinitely small while this guy is getting infinitely large. So the control that the eigenvectors have over the system changes from one to the other as time goes on, and that is called a saddle point. So 16 is C. Let's find a solution to this differential equation system. X prime equals ax. We need the eigenvalues. That's gotten by solving 2 minus lambda times 1 minus lambda minus 6 is equal to 0. Lambda squared minus 3 lambda plus 2 minus 6 is minus 4 is equal to 0. So lambda minus 4, lambda plus 1 is equal to 0. Lambda is equal to 4 and negative 1. 4 lambda is equal to 4. A minus lambda I is negative 2, negative 3, 3, 2. We can simplify that down to 1, negative 1, 0, 0. And so we get an eigenvector of 1, 1. For lambda is equal to negative 1, a minus lambda I gives us 3, 3, 2, 2. We can simplify that to 1, 2/3, 0, 0. So we get an eigenvector of negative 2/3, 1. We can multiply both of these entries by 3, and we get negative 2, 3. Okay, looks good. Let's solve for our initial condition, because we know at this point that our solution is going to be in the form x of t is equal to c1 v1, which is 1, 1, e to the lambda 1t, e to the 4t plus c2 times v2, e to the lambda 2t. Plugging in 0, 0 and setting that, plugging in 0 for t and setting that equal to 5, 0, we see that 5, 0 is equal to c1 times 1, 1 plus c2 times negative 2, 3. As a result, we can make an augmented matrix. 1, 1 minus 2, 3. Some linear combination of those two vectors is equal to 5, 0. Let's subtract row 2 from row 1. That gives us 0 here, negative 5 here, so we can make this a 1, negative 1. Let's subtract 3 row 1s from row 2. That gives us 0 and 3. So x2 is equal to negative 1, so we can make that a positive and switch the signs in here. And then x1 is equal to 3. So we're looking for 3e to the 4t, 3e to the 4t, so we agree with those two. And then we're looking for 2, negative 3 e to the negative t. So B is our answer for 17. 18. Which of the following subsets of the vector space R3 are subspaces of R3? So in order to be a subspace of R to the n, we need to satisfy 3 properties. Any set needs to be closed under vector addition, closed under scalar multiplication, and it needs to include the 0 vector. So let's take a look at number 1. It's the set of all vectors with components x, y, z with the property that 2 times x times y times z is equal to 0. It's a little difficult to see what this is, what this looks like visually right off the bat, but if I draw this out, it might help a little bit. So x, y, z equals 0, what we can interpret that as meaning is that either x, y, or z has to be equal to 0, or a combination of two of them must be 0, or all three can be 0. So that gives us the coordinate planes here, the xz, xy, and zx planes, along with the coordinate axes, so the zx and y axis, and the origin. If we take a vector from two opposing planes and add them together, we get a vector that kind of comes up out of the screen at us. That vector will be living in the first octant instead of in one of the coordinate planes. Thus, we've escaped our set, and this guy is not closed under vector addition. What about 2, the set of all solutions to this equation here? Well, what is that equation? That is just a plane that passes through the origin because it's equal to 0, so that x, y, and z can all be 0 and still satisfy that equation. We know that anything that we can express as a span is a valid vector space, and because a plane through the origin is exactly what the span of two linearly independent three-dimensional vectors would look like, that is a perfectly fine and valid vector space. What about 3, the solutions to this system here? Well, this is just like saying the solutions to AX equals 0, which is the null space, and we know that the null space of A is a subspace of R to the number of columns of that matrix. So because we have 3 columns, and this is the null space, and this is a subspace of R3. If we had a fourth column here, that would not be valid. As a subspace of R3, it would be a subspace of R4 instead. What about 4, the set of all of the solutions to this equation here? Well, I'll reuse this graph that we already had going down here. What does this thing look like in 3 dimensions? Well, it will have an x-intercept that is not equal to 0. X equals 1 is the solution when when y and z are equal to 0. When z and x are equal to 0, y is equal to 1/3, and when x and y are equal to 0, z is equal to -1/2. So hopefully you can see that 0, 0, 0 is not a solution. It's not a solution here. So if we take any vector in this set, and this plane would span all over the place, and I'm terrible at drawing that. But you can see it doesn't pass through the origin, so we take any vector that's in that set, multiply it by the constant 0, and we've escaped the set. And so that's why including the 0 vector is important. So that is not closed under scalar multiplication. Okay, so 2 and 3, nope, not 3 and 4. 2 and 3 are our solutions, so 18 is A. Let's determine a basis of the set spanned by these vectors. So we're looking for the column space of the matrix formed by smushing all these vectors together, and what we'll do is row reduce that matrix, see which columns have pivots in them, and then go up here and choose those corresponding columns as our solutions. And I think the answer, if I remember correctly, the answer is 1, 3, 4. So I'm just going to leave that up there. That'll be funny if that is correct. 1, 2, 3, 3, 6, 9, 1, 3, 5, 5, 11, 17, 2, 7, 12, 2, 0, 0. Don't you just love reducing this kind of thing? This is great. Awesome. Let's subtract 2 row 1s from row 2. That gives us a 0, 0, 1, 1, 3, -4. Okay, let's subtract. Oh no, we don't need to do that actually at all. Let's subtract 3 row 1s from row 3. That gives us a 0, 0, 2, 2, 6, -6. So this can be 1, 1, 3, -3. Let's subtract row 2 from row 3. That gives us 0, 0, 0, 1, and there we go. So we have our 3 pivot positions. My guesses were, it wasn't a guess, it was just, I circled some of them. That was wrong. It looks like our pivot positions lie in columns 1, columns 3, and column 6. And so 1, 3, 6, these guys right here will form a basis for the column space of the span of all those guys. So 19 is E. 20, Gram-Schmidt process. Gram-Schmidt process time. So we're looking for the third basis vector here, so we have to go through the entire process, which they usually don't make us do for these kinds of problems, so that sucks a little bit. We can find our first basis vector v1, and I'll call these, they want these to be called u1, u2, u3. Because of the way I usually write these out, I'm not going to go by their rules. We're going to call these v1, v2, and v3. We're looking for v3, and these are called u1, u2, u3. Okay, so v1, we can just normalize u1 up here, and we'll have an orthonormal basis vector. So the magnitude of u1 is 6, so we can take 1 over root 6 times 1 to 1 as our first basis vector. Now our second basis vector will be u2 2, 1, negative 1, minus the projection of u2 onto v1. So we have to subtract u2 dot v1 over v1 dot v1 multiplied by the vector v1. You'll notice that this 1 over root 6 will be multiplied once on the top, twice on the top, and twice on the bottom. So we can actually completely ignore that and just deal with the vector values in there. So u2.v1 will be 2, 4, minus 1 is 3. v1.v1 is 4, 5, 6. So we get 1/2 out here. And then v1 is 1, 2, 1. We can get rid of this negative 1/2, or sorry, that 1/2 by multiplying this guy by, or both of them by 2. So that gives us 4, 2, negative 2. Let's subtract that guy out. We get 3, 0, negative 3. We can simplify this down to 1, 0, negative 1 and normalize it by multiplying it by 1 over root 2. So there's our v1, there's our v2. The last step is to find v3. That will be u3, 3, 2, 2, minus its projection onto v1, minus its projection onto v2. So that's minus this expression, u3 dot v1 over v1 dot v1 multiplied by the vector v1 minus u3 dot v2 over v2 dot v2 multiplied by the vector v2. So u3 dot v1, remember we can completely ignore this 1 over root 6 for this entire process. That gives us 3, 7, 8, 9. v1 dot v1 we already saw is 6. Is that correct? 3, 6, 9. Okay, yep, we're good. And then v1 in here is 1, 2, 1, 2, 1. There. Again, disregarding the 1 over root 6. Okay. u3 dot v2 will be, yet again, disregarding the 1 over root 2, is 3 plus 0 minus 2, so that's 1. And then v2 dot v2 is 1 plus 1 is 2. And then we can replace this with 1, 0, negative 1. This becomes 3 over 2. Multiplying all these vectors by 2, we get 6, 4, 4, like that. We can multiply this 3 in here and get 3, 6, 3, 6, 3, and we're subtracting this guy. Okay, so this overall should give us our third our third basis vector, which we can well, it won't give us our basis vector, it will give us a non-normal version of that basis vector, which we'll have to normalize. So 6 minus 3 minus 1 is 2. 4 minus 6 is negative 2. 4 minus 6 is negative 2. And 4 minus 3 plus 1 is 2. So normalizing this, we will get 1, negative 1, 1 over root 3. And this is our V3. And looking around, C looks like our answer, which it is. Let's find the least squares solution to this inconsistent system of equations right here. So finding least squares is the same thing as solving A transpose A. X is equal to A transpose B. So multiplying A transpose A, we're multiplying 1, 2, 1, 3, 2, 5 by 1, 2, 1, 3, 2, 5. We're multiplying a 2 by 3 by a 3 by 2, so we will get a 2 by 2 matrix out with entries 6, 3, 4, 7, 12, and this is symmetric always, so we'll get a 12 there as well. And then 9 plus 4 is 13. 9 plus 4 is 13, plus 25 is 38. That's a 36. 38. Now A transpose times B is 1, 2, 1, 3, 2, 5 multiplied by 0, 5, 8. This is a 2 by 3 times a 3 by 1, so we will get a 2 by 1 result. 10 plus 8, we'll get 18 here, and 40 plus 10 is 50 here. So as a result, we can set up an augmented matrix to solve this system with 6, 12, 18 here, and 12, 38, 50 right there. And let's see, we can divide row 1 by 6. We get 1, 2, 3, and let's subtract 12 row 1s from row 2. That gives us 0. 38 minus 24 is 14. And then 12 times 3 is 36. And we get 14 here. Great, that gives us 1, 1. Now subtracting from here, we get a 1 for x1 as well, and our solution is just this right-hand side, which I don't know why they're writing them as row vectors, but we should get B as a correct answer, which we do for 21. Number 22, I'm going to try to do this one with least squares because for whatever reason the normal method of taking y minus the projection of y onto u minus the projection of y onto v is not cooperating for me. Most likely due to my own faults. Okay, so least squares really involves if we have some inconsistent system ax equals b, where here a will be negative 2, 0, 0, 1, 2, negative 1. So the span of these two columns is the same as just these two vectors in a span, which is w, times x is equal to negative 1, negative 5, 10. And if we solve this system where here's our A, here's our B, if we solve A transpose A, x equals A transpose B, we will get this B, our solutions for x1 and y1, actually x1, x2, and x3, will be the least squares solution, which corresponds to the orthogonal complement of y. Then we can subtract that from y, find its magnitude, and we should be good. So knowing that these are A and B, finding A transpose A, we have negative 2, 0, 0, 1, 2, negative 1, multiplied by negative 2, 1, 0, 2, 0, negative 1. This is 2 by 3 times 3 by 2, so we get a 2 by 2 matrix with entries 4, negative 2, negative 2, and 1 plus 4 is 5, plus 1 is 6. Okay, so there's that. Then let's compute A transpose, negative 2, 0, 0, 1, 2, negative 1, multiplied by B, which is negative 1, negative 5, 10. This will give us a 2 by 1 matrix with entries 2 and, what is this? Minus 1, minus 10, so minus 21. So now we can solve the, if we're really saying this times x is equal to this, we can set up an augmented matrix with 4, negative 2, negative 2, 6, 2, negative 21. Okay, let's divide this guy by, let's divide row 1 by 2. We'll get 2, negative 1, 1. Let's add that to row 2. We get 0, 5, negative 20. So we get negative 4 there, and we can add that. We can add that to row 1. We get 0, negative 3 halves. Okay, so those are our solutions. Those are our solutions there. Negative 3 halves and 4. Okay, so what I said earlier was slightly wrong. I said that this would be our solutions for x1 and x2 would be the orthogonal complement of y. Well, that's not exactly true. Really what this means is that negative 3 halves times this minus 4 times this is the orthogonal complement of y. So let's try to compute that if we can. So we're taking negative 3 halves times u, and this is y hat, by the way. Negative 3 halves times negative 2 is 3, and then these other ones are still 0. And then we are subtracting 4 times 1, 2, negative 1. So we have 3 minus 4, so negative 1. 0 minus 8, which is negative 8. And 0 plus 4, which is 4. Okay, there is our y orthogonal. Let's take y minus y orthogonal. Y minus the orthogonal complement of y, and then the magnitude of that should be the distance from y to this subspace. Negative 1, negative 5, 10, minus negative 1, negative 8, 4. I'll flip these signs around. And what do we get? We get 0, 0, 3, and 6. And the magnitude of this is the square root of 9 plus 36, which is the square root of 45. And the square root of 45 is equal to 3 root 5. Thank God. I have no clue why that wasn't working for me before, but really what this says is, you know, sometimes you do what you got to do. This is more work than that other method, but hey, we got there in the end. So 22 is E. Yeesh. 23, let A be an n by n matrix. Which of the following statements is not equivalent to the fact that A is invertible? So, invertible matrix theorem time. If A is invertible, are the columns of A linearly independent? Yup, because A needs to have n pivots, one pivot for each column. Is A diagonalizable? Well, this isn't the invertible matrix theorem, but we know that invertibility does not imply diagonalizability, and that diagonalizability does not imply invertibility. And we've seen that multiple times with matrices that are invertible but aren't diagonalizable, and matrices that are diagonalizable but aren't invertible. So, nope. What about 3? The columns of A form an orthonormal set. Here you go. Here is a matrix that is invertible. 1, 7, 3. Oh, shit. Sorry. Whoops. No. I meant to make a matrix that was invertible. That one was not. What about 10? Don't know how I managed to do that right there. But here's an invertible matrix. Are the columns an orthonormal set? No. The magnitude of the first column is whatever that is, root 50. The magnitude of the second column is root 109. So Nope, those are not equal to 1. The magnitude of the columns is not equal to 1. Okay, what about 4? The dimension of the null space is 0. Yup, because an invertible matrix must have n pivots, and as a result, its rank is equal to n. And since n is the number of columns, if we're solving our rank, which is n plus the, oh no, that's nullity, there we go, is equal to the number of columns, which is still n must be equal to 0. So that's true. The system ax equals b always has a solution for any b in Rn. This is true because invertible matrices, the transformations represented by invertible matrices, are always onto and one-to-one. So there is both a solution for all b in Rn and a unique, that solution is unique. So 1, 4, and 5, 1, 4, and, oh wait, did I do this wrong? 1, 4, 5. Wait. Not equivalent. Oh, okay. So our logic wasn't wrong, but these two are not equivalent, so our answer is 2 and 3. Whoops. So 23 is C. 24. Let C from -1 to 1 be the space of all continuous functions over that interval with an inner product defined here, where it's the integral from -1 to 1 of f times g for the dot product of f and g. It's really not the inner product of f and g. Which of the following sets is an orthonormal basis for this span right here? So that means we are, oh God, we're applying the Gram-Schmidt process, minus the normalization step at the end, but we're using both polynomials and a different non-standard inner product. So Gram-Schmidt process always begins. We can call these U1, U2, and U3. What we can do is just say that V1, our first basis vector, is just equal to U1, and since we don't have to normalize anything, we can just leave that here since we're looking for an orthogonal basis, not an orthonormal basis. So now V2 is equal to U2, which is t minus 1, minus the projection of t minus 1 onto V1. So that's going to be minus U1 inner producted with, sorry, not U1, and I should be clear, this U1 is 1. There we go. The inner product of U2 and V1, so that is t minus 1 and 1. So we're going to have to compute that. And then on the bottom, we just have the inner product of V1 and V1, and we're multiplying all of this by V1. So let's go compute. Let's go compute this up here. So this top bit is going to be the integral from -1 to 1 of t minus 1 times 1. So t minus 1 dt. Because t is symmetrical in such a way such that since we're integrating evenly to the left of the y-axis, and to the right of the y-axis, the area contributed by any odd function, so a function with an odd exponent, you know what I mean. So like x cubed, if we get any x cubeds, that will also contribute nothing to this integral overall, and that'll save us a little bit of time in the end, because all we're really doing is doing this right here. So negative t on 1 to -1 is -1, 1, so we get -2. -2 up there. And then the dot product of 1 and 1 is just the integral from -1 to 1 of 1 dt, which is t on 1 to -1, 1, -1, so we get 2. Great. So evaluating this, we get t minus 1 plus 1, or just t, which is our second basis vector. And so far all of our answer choices except for that one and that one actually, agree with us. Okay, let's find our third basis vector. V3 is going to be U3, so t squared minus t minus U3 dotted with V1, and then we're dividing that by V1 dotted with, or inner producted with V1. I'm not really sure which one they want us to say. All multiplied by 1, then we need to subtract out U3 dot V2 over V2 dot V2 multiplied by V2, which we know now is T. So all of these are T's, T, 1, 1, 1, 1, 1, and then U3 is T squared plus T. So this top inner product we can find as the integral of t squared plus t dt. Well, we know that this t is going to contribute nothing, so really we're just integrating t to the cube, t cubed over 3 on -1 to 1. This gives us 1/3, -1/3, so we get 2/3 up here. Additionally, we know that the dot product, or the inner product of 1 and 1 under this new inner product space is 2. So I'll replace that there. And since we have 2/3 over 2, this just becomes 1/3. And right off the bat, we know our answer because that's the only one with the 1/3 in it that we're looking for. But let's make sure that this evaluates to plus t for the rest of everything in this answer choice to make sense. So we're subtracting this guy over t dot t. So this will be u3 times t, which is t cubed plus t squared dt. T cubed has an odd exponent, so we can just get rid of it. We're integrating from -1 to 1. This is t cubed over 3. Wait, we already know what this one evaluates to. This one's 2/3. 2/3. Then t and t there on the bottom will be the integral from -1 to 1 of t squared dt. This gives us t cubed over 3. Oh wait, we already know how to do this one. This is just 2 over 3. So this gives us minus t, and when we compute all this out, we get t squared minus 1/3, because we have minus t and, oh wait, minus t, and we should, oh, I wrote that wrong, that's why. This is t squared plus t right there. Okay, plus t minus t, we get t squared minus 1/3. So E is our answer for 24. Okay, here we go. It is time for orthogonal diagonalization. So let's get going. If we are finding a diagonal matrix D, just like the normal diagonalization that we learned for midterm 2, it will be composed of the eigenvalues of A along the main diagonal. But then for our invertible matrix Q, where because this matrix ends up being symmetrical, its inverse is equal to its transpose, so that's why we can write it like that. What these columns are going to be is not directly the eigenvectors, but the normalized basis vectors for the normalized orthogonalized basis vectors for the eigenspaces corresponding to our eigenvalues over here. So what that means is if we had 3 unique eigenvalues, all we would need to do is diagonalize normally, and that it didn't mean for that to be a pun, because the next thing and the only thing we'd have to do after that is normalize all of our vectors here. You see all these vectors in our Q's, besides this one, so we know that this one's wrong, are all normalized. So then the other thing that the spectral theorem of symmetric matrices tells us is that eigenvectors that come from different eigenspaces as long as the vector that we're diagonalizing is symmetrical, which this one is, those eigenspaces are automatically and always orthogonal. So that means the only orthogonalization that we need to do is when we have a double eigenvalue, or an eigenvalue with a multiplicity greater than 1. So it'll have multiple eigenvectors corresponding with it, which it looks like we do have in this case. So we'll need to make sure that that happens. Okay, let's solve for our eigenvalues. So it would be very nice if they gave them to us, but they are not that kind. So let's find the eigenvalues of A. It's going to be a little bit of a pain. We're finding the determinant of A minus lambda I, so that's negative lambda 1, 1, 1, 0, nope, not 0, negative lambda 1, 1, 1, negative lambda. Okay. Ugh, this is going to be a slog. So we can split this up as negative lambda times the determinant of this submatrix minus 1 times the determinant of that submatrix plus 1 times the determinant of that matrix right there. So that will be negative lambda times negative lambda 1, 1, negative lambda plus 1, minus 1 times 1, 1, 1, negative lambda plus 1 times the determinant of 1, 1, negative lambda 1. Okay, great. This is equal to negative lambda times lambda squared minus 1. Then we're subtracting negative lambda minus 1, and we are adding 1 plus lambda. This gives us negative, I don't like dealing with this, negative lambda cubed. Is there not just an easier way to find these? Yuck. And they keep varying them in the answer choices too, so although if this was a real exam, you'd go look and see that C, D, and E, and even B all had the same eigenvalues. So we should get negative 1, and 2 in the end, but I think we have to do this. Negative lambda squared plus lambda plus 1 plus 1 plus lambda, so we get negative lambda cubed plus 3 lambda plus 2 is equal to 0. And let's see, if we take what we think our eigenvalues are, lambda plus 1 squared times what? Lambda minus 2, we should end up getting that, or negative 1 times that, as it looks like we will. So this will be lambda squared plus 2 lambda plus 1. We're multiplying that by lambda minus 2. We will get lambda cubed plus 2 lambda squared plus lambda, and then minus 2 lambda squared, minus 2 lambda squared, minus 4 lambda, minus 4 lambda, minus 2, and all that's equal to 0. So we get lambda cubed minus 4 lambda, minus 3 lambda minus 2 is equal to 0. So there we go. We got negative 1 times this thing. So that means that we could factor this thing and get this right there. So we know that after all that stupid work, we know that lambda is equal to negative 1 with a multiplicity of 2 and 2. For lambda is equal to negative 1, we get 1, 1, 1, 1, 1, 1, 1, 1, 1. Great. We can simplify this down to 1, 1, 1, 0, 0, 0, 0, 0, 0, and pull an equation out of this. This is x1. Since all of this is equal to 0, this is x1 plus x2 plus x3 is equal to 0. So instead of finding our eigenvector normally, we're going to have to do something a little weird because we're dealing with a multiple eigenvalue here, and we want to make sure that the eigenvector that we get is orthogonal. Or sorry, the two eigenvectors that we get from here are orthogonal, so that they're a basis for this eigenspace. If x1 and x2 are 1, then this is satisfied by 1, 1, negative 2. So 1x1 plus 1x2, plugging those in, we have 1 for x1, 1 for x2, negative 2 for x3. That does solve it. Now what's a vector that also solves this equation but is linearly independent? Well, let's flip either x1 or x2. Why not? Let's just flip x1. We have negative 1. We'll keep a 1 there. And then, as a result, we can get 0 for x3. So these are two vectors that lie in this eigenspace that are linearly independent because they're not direct multiples of each other. And so we can use these as, once we normalize them, as a basis for this eigenspace. So as a result, our two columns corresponding with lambda equals negative 1 will be 1 over root 6, 1 over root 6, negative 2 over root 6, negative 1 over root 2, 1 over root 2, and 0. And if we go look up here, we should see some kind of evidence of this going on. Negative 2, yeah, so I'm seeing stuff that we agree with in answer choices. Yeah, in answer choices D and E. So let's make sure that these work. What is the difference here? Okay, actually we know our answer right now. So if we multiply this vector by negative 1, which would make it still a basis vector, we get this vector here, which we know corresponds with lambda equals negative 1. And then right here we have exactly this other vector that we found. Wow, look at how that works out. And that corresponds with negative 1. And what they've done here is they have the two vectors in the right spots, except that D is a little mixed up, where we should have negative 1 here, but we have a 2 instead. So let's solve for the basis vector for the eigenspace corresponding to lambda equals 2, just to make sure that we get 1/3, 1 over root 3, 1 over root 3, and 1 over root 3. So for lambda equals 2, we will get negative 2, 1, 1, 1, 1, negative 2, negative 2, 1, 1. Okay, let's add two row 2's to row 1. That gives us 0 here, negative 3 here, and 3 here. We can turn this into 1, negative 1, and add 2 of it to row 2. That gives us 0 and negative 3, and let's add 1 of it to row 3. That gives, subtract 1 of it from row 3. That gives us 0 and, 1, 1, negative 2. Subtract it, 0, negative 1. We can subtract row 1. Oh no, I'm getting 3 pivots, aren't I? Did I do this right? Okay, I'm not gonna cut here. I just need to make sure that we have this. Negative 2, 1, 1, 0. Nope, it's not a 0. 1, 1, 1, negative 2, 1, negative 2. Let's go about this a slightly different way. Let's subtract row 2 from row 3. That gives us 0, 3, negative 3. Here's our 1, negative 1. Let's add two row 2's to row 1. That gives us a 0 here, a negative 3 here, and a 3 here. Okay, so there we go, 1, negative 1. That lets us set this to 0, 0. I made some algebraic mistake that last time. And we are almost ready to solve here. Let's add two row 1's to row 2. That gives us a 0 and a negative 1. So we see that our eigenvector is in fact 1, 1, 1. We can normalize that to 1 over root 3, 1 over root 3, 1 over root 3, and this terrible, terrible problem is done, and our answer is E. Okay. Yeah, God, that was brutal. Okay, well, and this entire test was brutal for me too, but now we're done.